So we're going to find the period of a uniform stick, okay, like a meter stick, pivoted about 1 inch. So imagine I have a hole drill at the end, okay? I'm ignoring friction. Going to pull this thing back and I'm going to let it oscillate. Okay, so it's a physical pendulum. So that's our expression that we've had previously for a physical pendulum, okay? Remember, you have to remember what the I is, all right? So that's the moment inertia of the object about axis of rotation, or axis A. M is the mass of the thing rotating. Okay, here's just one object. And D, remember, D is the distance from the pivot point to the center of mass. Okay, so we have to know all the variables in that expression. Okay, so D in this picture, okay, there's the center of mass, stick is length L, so D is L over 2. Okay, so D is L over 2. All right, and the moment inertia, it's a stick about 1 in, so moment inertia about axis A is 1/3 ml squared. Okay, so we know that. Okay, and then there's mg, and then d was our L over 2. Okay, so I cancel the m's, careful, one of the L's go away, the 2 flips up on top, and that gives me the period of the meter stick. Okay, now what you could actually do is you could take a meter stick, or you don't have a meter stick, you have a yard stick, okay? You could drill a hole about the end, pivot about the end, okay? You can do this, you know, where you are now. And obviously you measure the length, in case it's a yardstick, or any thin stick. You can actually do this even if you have a thin rod, okay? If you have a hiking stick, okay, that might work, okay? It's not perfectly uniform, okay? But the idea is you can pivot it. You can measure the period with a stopwatch, okay? All right. Now, if you're doing it with your fingers, okay, pivoting the stick, or you're trying to pivot your pencil about one end, there might be a lot of friction, so you might not get 10 good oscillations, so maybe do 5 or so. So measure maybe 5 periods, divide by 5, okay? So you have the period, you know the length, okay? Rearrange this, and you can actually get an experimental value for G, okay? So another way to measure little g, you can measure with a meter stick. Okay, so now we want to do is we want to find what would be the length of a simple pendulum that has the exact same period as the meter stick about one end. Okay, so what we're asking is we want a simple pendulum. Okay, there's our simple pendulum, but we want the period of the simple pendulum to be the same as the period of that stick. Okay, so essentially what we're saying is we want the period of the simple pendulum. Remember, the period of the simple pendulum is 2 pi, right? 2 pi square root of L over G, all right? And we want that to be equal to the period of that meter stick, which is my 2/3, or 2 pi times square root of 2/3 L over G. So I just compare the left side and the right side. That says that that little L, okay, has to be equal to 2/3 big L, right? Just compare the two sides, or just square both sides and solve for little l, okay? So what I'm going to do now is I'm going to show you a video. Is I'm going to have a meter stick, okay? So I'm going to have my meter stick there, okay? And then I'm going to have a simple pendulum that's length 2/3 L, okay? And I'm going to pivot them both back and forth about the end, okay? And you're going to see that they have the same period. Okay, so this simple pendulum, whose length is 2/3 of a meter, or 2/3 L for that stick, all right, has the exact same period as the meter stick, all right? So I just redrew them here. So here's the meter stick, okay? It's easier to think of a meter stick, okay? Because 1 meter is a nice number, all right? It's a meter stick. And then the simple pendulum is length 2/3 L, right? Or 2/3 of a meter, right? 66.67 centimeters, all right? So I just hung them side by side, and now I'm going to go over to the meter stick, and I'm going to put a little piece of tape, okay, right on that part of the stick, right, 2/3 of the way down, okay. So 2/3 of the way down, okay? So that point has some significance. That point is given a special name. That point P is called the center of percussion, and some books call it the center of oscillation. Okay, both of those mean the same thing. So that point P is the center of percussion for our pivot point A. Okay, now why am I specifying that point? Why am I calling attention to that point? Okay, let's see. Now I'm going to do is I'm going to take this stick, okay, that point P, I'm going to drill a hole, okay? I'm going to drill a hole through that point P, right there. I drilled a hole through that point P, and then I'm going to pivot it about that point, okay? So let's say I put it on a nail, all right? And I'm going to bring it back a little bit, and I'm going to oscillate it back and forth, okay? So this is now a physical pendulum, but it's now pivoted at that point called the center of percussion, okay? So remember, if that was 2/3 L, right, then this part up here is 1/3 L, okay? Okay, so we're gonna pivot at that point, and I wanna calculate what's the period about that point P, right? That point P right there. Okay, so let's calculate that. So I wanna calculate the period about point P. Okay, that's our starting point for a physical pendulum. Okay, the top point, the top part, the numerator, is the moment inertia about that point P. Okay, well that's a meter stick about some other point, so I have to use the parallel axis theorem. So remember, parallel axis theorem is I center of mass, so for the stick is 1/12 ml squared, plus mh squared. Okay, where h is a distance between the pivot point and the center of mass, okay? That's h. Okay, now how did I find h? Well, that much of it to the center of mass is L/2, okay? So h is equal half of the stick, right, that L/2, minus that portion, minus L/3. Common denominator is 6, so I got a 3 and a 3 and a 2 and a 2. So 3/6 minus 2/6 is 1/6. Oops, 1/6 L. Okay, so that's where that sixth came from, all right? So in the parallel axis theorem, that h is the perpendicular distance between these two parallel axes. Okay, so the center of mass axis points out of the screen, the axis P points out of the screen. The distance between them is h, L/6. So that's what goes, okay, that's what goes right there from the parallel axis theorem, okay? Okay, then the bottom, okay, that mass is the mass of the whole thing, which is the stick M. There's a G. And remember D. Okay, D does not stand for diameter. Okay, D in that derivation, okay, we did that in the notes. D is the distance between the pivot point and the center of mass. Okay, that's the distance D between the pivot point and the center of mass. That's just L/6. Okay, now just clean this up. The M's go away. Okay. One of the L's go away, all right? And then in terms of the algebra, I have a 12th on the top plus a 36th on the top, okay? That 6 would come up on top, and I have 6/12 plus 6/36. So I have 1/2 plus 1/6, okay? And then common denominator is a 6. I got a 3 times a 3. And then I have 4/6. So in the square root, I'd have a 4/6, and that reduces to 2/3. So that's where that 2/3 came from. Okay, so no big deal. All right, so just look at the algebra on that. Okay, so the bottom line is what did we do? Had a meter stick, found the period was that. Okay. I found the simple pendulum, the length of the simple pendulum that had the same period. Okay, that length was 2/3 of a meter, or 2/3 L. Okay, all right. So I lined them up. I drilled a hole at 2/3 the way down. I now pivoted at that point, right, which is 1/3 of the way down. Pivoted at that point, and I found the period to be the exact same. Right. So here's our period up here. Right, that's our period. 2 pi square root of 2/3 L/G, and here's the period of this stick about the center of percussion. It's the exact same. okay? So that's the significance of that point, the center of percussion. That says that the stick has two different places that you can pivot it, and it has the same period. You can pivot it about the end, you call it the 0 point, okay? And you can go down 2/3, pivot it from there, and it'll have the same period, okay? So really on the stick, you could go down 1/3 right there and drill it, okay? Or just go down to the 2/3 point and drill it and invert it, okay? So, okay, what's the significance of that point, all right? So that center of percussion point, all right, it turns out that if a quick force, right, okay, an impulse, right, so if a quick force acts at the center of percussion, no reaction force occurs, okay, or if you're holding it there, no reaction force is felt at the pivot point A. So imagine you're holding the stick, okay, a quick force occurs at the center of percussion and you're holding it and there's no reaction force, okay? What would be an example of that, okay, a quick force, okay? What about a baseball hitting a bat, okay? So consider, I take a stick, all right, and imagine this stick is pivoted at one end. So in other words, I have a hole drilled, okay, there's a hole drilled, okay? And instead of hanging it on a nail, I'm going to hang it on a string, okay? So I'll show you a video of that meter stick hanging from the end on a string that's supported, that goes through the hole. Okay? And what we're going to find is if I give that stick a whack, so I exert a big force of it, I think I use a metal bar. So you hit the stick right at the center of mass, okay? Well, Newton's second law says, what does Newton's second law say? Newton's second law says, okay, center of mass, that instant that the force is in contact with the center of mass right there, if the net force is to the right, center of mass is going to accelerate to the right, okay? And the tip of the stick at point A is going to start to move to the right. It's going to translate, okay? Now, there's not going to be any rotation because I'm hitting at the center of mass, all right? So I'm going to show that in the video. Now, let's say I hit the stick over here, okay? A little bit closer to the axis of rotation where the string is, okay? Well, this end of the stick is going to do two things, okay? It's going to move to the right, okay, because it's going to translate, okay? Remember why that happens? While the force hits the stick that short time, Newton's second law says if the force is to the right, okay, that the center of mass is going to start to move, okay, to the right, okay? So there's a translational speed due to the stick moving to the right, and there's a rotational velocity, okay, due to the stick rotating, in this picture, clockwise, okay? All right, so if you're holding it here with your hand, that stick would be forced out of your hand to the right, okay? All right, now if I had hit the bat or the stick instead at the bottom, okay, so if that force acts instead at the tip of the stick, okay, Newton's second law says that while the force is in contact, okay, or the ball's in contact with the bat, or the rod I'm using is in contact with the bat, so the force is to the right, so the center of mass will accelerate to the right. So the tip of the stick is going to have some translational velocity to the right. So there's some translational velocity, okay, but due to where the force is acting, the stick is going to start to rotate counterclockwise. So you have a translational velocity to the right of the end of the stick, and you have a rotational velocity to the right, okay? So the way where the force is acting at the bottom of the stick, that rotational speed is going to be bigger than the translational speed. So if you're holding on to the end of the stick, okay, the stick is going to tend to move to the left out of your hand. It'll be yanked out of your hand to the left, okay? Here the force is acting closer to the center of mass, so the translational speed is bigger than the rotational speed of that tip. Okay, so again, if you're holding the stick here, okay, the stick is going to be yanked out of your hand to the right. Okay, all right. Then the other thing I'll show in the video is now I'm going to hit the stick with a force right at that center of percussion. Okay, so while the force acts, okay, the center mass is going to move to the right, accelerate to the right. So the tip of the stick, okay, that's going to have a translational velocity to the right. Okay, but the tip of the stick is going to tend to rotate counterclockwise. Okay, so there's going to be a rotational velocity to the left. Okay, so these two velocities, okay, are going to be equal and they cancel out. Right? So if I'm holding it, okay, I'm holding the stick at the end, okay, that when this force impacts at the center of percussion, the tangential acceleration, this tip, okay, which way is it going to accelerate? Okay, this tip has no tangential acceleration. Okay, it's zero. So if you're holding on to it, the reaction force, okay, well, if you're holding on to it, you're not going to feel a reaction force. So no reaction force would be felt at the tip of the stick at the point you're holding. All right. So I'm going to show a video, and when I hit it at the center of percussion right there, this tip of the stick, okay, doesn't yank to the right or yank to the left. It pretty much stays in the same position for a little while the whole stick rotates around. Okay, so for a baseball bat, sometimes they call that the sweet spot. So let's take a look at that video. So in the video, okay, the first one you saw would be an example, here maybe I'll use that color, would be if the ball was coming in that direction, okay, and you're holding it, okay, so this is where the ball would hit the bat close to your hands. So the ball, where the ball hits the bat, it wants to jam it into your hand. So the bat is being pushed into the palm of your hand. You're being jammed, okay? The second time I hit it down here, okay? If you're holding on to the bat, then the bat comes flying out of your fingers, okay? The third time I hit it at the center of percussion, okay? And if you're holding it, okay, the ball would be coming in like that. Oops, I forgot to draw that one, okay? The ball will be coming in like that, right? And again, your hand is moving, right? As you swing the bat, your hand is moving, okay? So when your bat makes contact with the ball, even though your hand is moving while you're swinging the bat, this part of the bat is not yanked out of your fingers or jammed back into your hand, okay? The bat just keeps on swinging, okay? And you don't feel that reaction force, and it's easier to keep that bat moving, all right? So I'll show you a couple videos of where the ball hits the bat at about that point, and you can see that the bat likes to oscillate in certain modes, okay? The bat almost looks like a sine wave, okay? So when the ball hits that point, it likes to set the bat up into the mode of vibration or oscillation that's natural for that bat.
So in this shot, we see the full bat.
And the bat bends too?
This makes me feel like every single piece of equipment in baseball is made out of rubber. It's totally unexpected because we look at a bat like this and it feels totally solid.
Yeah, when you have a long object like a bat, it is going to have the ability to bend. We're seeing some vibrations that extend all the way into the hands.
Okay, so I want to look at how you install a door stop. Okay, why are we doing this? Okay, all right, so we just looked at the concept of center of percussion. Okay, and the idea is if you're holding the bat here, okay, the ball hits close to the bat is jammed into your hands. Okay, over here, if the ball hits the tip of the bat, okay, and you're holding the bat is yanked out of your hands. Okay, and it doesn't happen. I did these pictures up here for a bat. Okay, and it also works if you're playing tennis, right? If you sign up for a tennis or badminton class at Mesa, okay, especially tennis, right? Because the racket's heavy and the ball's coming in fast. Okay, so if the ball's coming in and the ball hits the end of the racket and you're holding it here, okay, right, when the ball hits that end of the racket, right, it's going to tend to take the handle, right, and rip it out of your hands, right? If the ball comes in close, all right, near your hands, that's going to take the end of the racket and jam it into your hands. Okay, that's going to hurt. Okay, so somewhere in here, okay, right in the middle, all right, is the sweet spot. Usually they put the emblem right there. Okay, so when the ball hits somewhere in the middle, all right, and your hand is bringing the racket through, the ball hits the racket, there's no reaction force felt down here. The racket's not yanked left or right out of your hand, and the racket just keeps on moving. Okay, so that idea, okay, also works for a door stop, all right? So imagine, going back to this picture up here, okay, imagine this is a door, okay, this whole thing is a door, all right? That would be the hinge, all right? And the door is going to close, okay, onto a wall, all right? So the door is going to close onto a wall. Okay, so let's look at this picture here. So here's the door stop, okay? And we want to know where along the wall, especially in this picture here, where along the wall do they mount the door stop? You ever notice where they mount the door stop? Okay, well, if you mount the door stop at point A, okay, so when the door closes, the door stop is going to hit the door somewhere around there at point A, okay? All right, that's like this picture here, okay? That's like a force acting at the end of the door, okay? Here's the hinges on the door, okay? So if the door hits the door stop down here, okay, that's going to tend to yank the hinges, the door and the hinges, in that direction. Okay, and the door and hinges are attached to the door jamb, okay, or the hinges are attached to the door. So that's going to tend to put stress on the hinge screws, okay? So in this picture here, the door closes, whacks the door stop, okay? That's going to tend to take these hinges, okay? Imagine the door is closed right there, okay? That's going to try to rotate the door, okay, at this point in that direction, okay, in the direction of the blue A, all right? Now, if you mount the door stop at point B, okay, now the force, okay, is close to the hand. So that would be this picture up here, okay? So here would be the door closing, okay, hits the door stop, all right? So that would tend to rotate the door, okay, or rotate the door on the hinge in that direction, okay? So looking back at the picture, if this door stop is too close to the hinges, when the door hits it, okay, then the door and the hinges, when that door is closed and hits the door stop, it's going to tend to yank the door and hinges in that direction. Okay, so at either points A and B, okay, when the door smacks into door stop A or B, these hinges, okay, those hinges right there are being yanked left and right. Okay, those hinges are being yanked left and right. So where do you mount the door stop? Well, it's not the exact same as what we did, but you can think a portion of that door is acting like a bat. Okay, so perhaps the center of percussion maybe is over here somewhere, okay, at point C. So when this door goes to hit that the door stop, okay, there's no reaction force felt on the hinges. So those hinges aren't yanked to the left and they're not yanked to the right. Okay, one way you could actually try that at home, okay, don't do this, okay, don't do it, okay, is you can loosen these screws a lot so that you can see the door wiggle, okay, and then you could put something here, maybe like a ball or something like that, okay, and slam the door, and you can watch the hinges try to yank the door that way, okay, or if the door and the hinges are tight and you loosen the screws on the hinges to the door jamb, okay, you're going to see the whole door try to move off, okay, or if you take something and put it over here, okay, and then slam the door, okay, where A is, you're going to see these hinges move into that door frame. Okay, so same idea of the baseball hitting the bat. That's one application of the center of percussion, that you want to mount the door stop so that the 2,000 or 3,000 times you close the door a year, it doesn't put a lot of stress on the hinges.
Just to test it. There you go, that's how you fit a wall and floor doorstop, as easy as that.